Right, to get the marks for this question, what I've put in here to help you see some additional information. Here's a reactivity series. Most reactive at the top, least reactive at the bottom. The positioning here determines the method of extraction. So carbon is really important because this shouldn't be there. It is not a metal. It's there as a reference point. Everything above carbon has to be extracted using electrolysis because they are more reactive than carbon. Anything below carbon, so this little group here, we heat them with carbon. Carbon is more reactive, and therefore carbon will displace them and give us the metal. The bottom two are unreactive and therefore just found uncombined. We don't have to do anything to get those, okay? So this question is picking on aluminium. Aluminium is above carbon, so I can't react it with carbon because carbon is not reactive enough. So I have to use electrolysis. And we need to just explain that in an answer. So I'm going to say that aluminium is more reactive than carbon. I'd put that into words. Aluminium is more reactive than carbon. So the carbon is not able to displace aluminium from its compound. It's not able to push it out and give us aluminium on its own. Some further bits to think about with this. So we've got here an extraction process. This is extracting titanium from titanium chloride, and they use magnesium because magnesium is more reactive than titanium to do this. So you can see the titanium's been displaced and the magnesium ends up with the chloride. In ionic form, this is what we've got. And it wants us to identify which of these has been oxidized, which of these has been reduced. Right, let's have a good look at this. So titanium here, let's zoom in a little bit. Titanium's gone from Ti4 plus to Ti. Right, how do I take something that's positively charged and turn it into something with no charge? I have to add electrons to that. Okay. Oh, hang on. We're doing it the other way around, aren't we? So how do I get something that's 4 plus to become no charge? Oh, that's right, yeah, we add 4 electrons. So we add 4 negative electrons. So let's put it into an equation. So remember, this is adding electrons, gain electrons is reduction, okay? So reduction reaction, we are taking titanium, 4 plus ions. How many electrons does it need to add? 4 electrons, and it will form titanium, and that is reduction. Let's look at the magnesium. So magnesium's gone from Mg, and it's going to Mg2 plus. How does it take something that's got no charge and make it something that's positive? I need to lose electrons. So this equation is magnesium, and it's going to become Mg2 plus. And how does it do that? By losing 2 electrons. So that is an example of oxidation. Why are these described as redox? Well, redox is because you have got reduction and oxidation happening at the same time in a reaction. Okay, having the same time in a reaction. So one chemical is being oxidized whilst the other chemical is being reduced, as we just saw here. Titanium is being reduced and magnesium is being oxidized. Therefore, it's a redox reaction. Write the formula for titanium sulfate. Let's use our method. So titanium is 4 plus, therefore it wants to make 4 bonds. Sulfate is SO4 and it's 2 minus, so it wants to make 2 bonds. Now before I swap these over, let's simplify. So it's 2 and 1. Then we cross. So titanium ends up with number 1. Don't need to write that down. The sulfate, SO4, ends up with a 2. Put brackets and put a 2. There's my formula for titanium sulfate. Okay. Right, the next one is a question that we've come across before, but we just need to make sure we've got the advantages and disadvantages. The advantages are kind of the same for phytoextraction and bioleaching, but the disadvantages are a little bit different. So phytoextraction, remember, it means using plants. Phyto is Greek for plants, so using plants. So the advantages of this are that we can use low grade ore. We don't have to use ore that's got lots and lots of metal in it. Okay, so often it's used to extract from waste or stuff that would be get thrown away. Second advantage is there is no need for mining. We don't have to dig great big holes, and that means so we get less visual pollution, or you could say we'd get less sound pollution or less carbon dioxide because we're not digging stuff up out of the ground. Okay. Disadvantages of phyto extraction, well, it's very slow. We've got to wait for plants to grow. And the other issue is it depends on climate for growth. So if you have got nice conditions, the plants will grow. If there's a change in the weather, then you could lose the crop and therefore you don't get the metals coming out of the ground. Bioleaching, these two here would be the same for this. So the advantages are, again, using low grade ore, and we don't need to mine, and therefore we get less visual pollution or less CO2, or less noise pollution from all the heavy machinery needed. Disadvantage of this, again, it's slower. And the other disadvantages is the bacteria that work in this process can release toxic chemicals, and we have to prevent those chemicals from getting into the environment and causing damage. And finally, the last one, or last couple, sorry, here, explain how we get copper from copper oxide. Right? If we go back up a second to reactivity series here, I can see that copper is below carbon. So what I'm going to do is use the fact that carbon is more reactive, and I'm going to heat the copper oxide with this. If I'm going to show this, I'm actually going to write the equation for that. So I'm going to say that copper oxide, and we're going to add carbon to it, and here we're going to heat this up, and that's going to lead to copper being formed. So there's my copper, and then the carbon dioxide, that's a displacement reaction. So the carbon is taking the oxygen because carbon is more reactive than copper. So your answer needs to say heat the copper oxide with carbon, and you get yourself the 2 marks. Okay, this one here was a difficult question. I've added a little bit here. It says, why is excess lead nitrate needed? So the lead nitrate's job in both reactions is to make sure that the iron reacts fully. So why do we need excess of this? It's to ensure that the iron reacts fully. I don't want any of the iron left at the end. I want it all to go. Then we've got 2 methods to do this, 2 equations, and it wants us to work out which method is going to be the right method based on the fact that we've got this amount of iron making this amount of lead. Different ways to do this. A good way to do this is I'm going to take the iron and the lead, and I know from the question it tells me there's 4.48 grams of this, and there are 24.84 grams of this. So that's the mass. I'm going to do an empirical formula style ratio here. So if that's the mass, what is the relative atomic mass? So the MR for iron, it tells me is 56, and this is 207. So I'm going to divide those numbers out. So this one here is going to give me 0.08, and this one here is going to give me 0.12. Divide by the smallest, so the smallest is 0.08, so divide by that, and then divide by that. That's going to give me 1, and that's going to give me 1.5. I can't have 1.5 an atom, so let's double all that. That's going to give me 2 to 3. There's my ratio, and if you go back up to the questions, equation 2 goes from 2 to 3. So equation 2, and state this. Now you've done the hard bit, then say equation 2 is correct, or the right one. Don't just leave it to them to guess that you know the answer. If you don't like that method, the other way to do this is a reactive mass calculation, and you would find out, you basically would test them both, and one of them would give you the right answer. So you'd work out here how many moles there are, work out the ratio, then convert the moles to this back into the mass, and it gives the same answer. This one will work, and this one wouldn't give you the correct information.